Okay, we're going to continue our probability discussions by talking about independent and dependent events. Two events are independent if the occurrence of one does not affect the occurrence of the other. For example, if we're talking about rolling dice and flipping coins, rolling a 3 does not make flipping heads any more or less likely. It has no effect, right? If you roll two dice, rolling a 2 on die letter A or whatever, the red die, does not make rolling a 5 on the blue die any more or less likely. They happen completely independently of one another. If you draw a card from a deck, put it back, and then draw again, what you got the first time makes no effect on the second, assuming we reshuffle or whatever. However, if I don't put that card back, I hold it while I draw a second card, that does change probabilities. And we'll talk about that a little bit later. So as long as we put it back, we call this replacement. The probability does not change. We'll see that here in a minute. Independent events have a probability that looks like this. The probability of A and B happening is just the product of the two events happening independently. Okay, so you just multiply the probabilities of the two events. It's pretty simple. So if I want to roll an even number on a die and then flip heads on a coin, all we have to do is multiply the probabilities of those things happening individually. So how many ways, well, on a die, there are 6 outcomes, right? How many of them are even? Well, there's 2, 4, and 6. So 3 of them are even. Times, how many outcomes for flipping a coin? That'd be 2. How many of them are heads? Just 1. So I multiply those together, I get 3 over 12, or 1 over 4, which is 25%. Probability of drawing a 2 and a 7 from a deck. We are going to assume that we replace the card. Otherwise, this is a different question, okay, which I alluded to earlier. So, drawing a 2. There are 52 cards in a deck. How many of them are 2s? Well, there's 4 suits, and there's a 2 in each suit, so there should be 4 of them. Times, and here's where that replacement comes in, how many cards are in the deck? Well, assuming I replace the first one, there are still 52 cards in the deck. How many of them are 7s? Well, by the same logic, there's a 7 for each suit, so there should be 4 of them. If I reduce those, I get 1 over 13 times 1 over 13, which would be 1 over 169, or 0.0059, which is 0.59%. Very unlikely. Okay, but you can see why that replacement makes a difference, because if I hold that card while I draw the other one, there are not 52 cards in the deck anymore. That changes things. Two events are dependent when the occurrence of one event does affect the occurrence of the other. Okay, so let's skip past all this and just look at the example real quick. A group of 4 students includes 1 boy and 3 girls. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. So how many ways can I draw 2 people out of a group of 4? That's what this table shows, right? I could get a girl and then a boy, or a boy and then a girl. I could get the girl-boy pattern again, but with a different girl. Notice there are 3 different girls. That's what these numbers are for. Girl 1, girl 2, girl 3. There's only 1 boy, so we don't need to put numbers by that. Or I could get just 2 girls, and there's 6 ways to get 2 girls. Okay. Now, the order we draw them in, whether it's girl 1 and then boy, or boy and then girl 1, matters because the roles are different. We have a speaker and a recorder. That's not the same job, so it does matter. Okay. So here's the probability. The probability of getting a girl first, of a girl first and a girl second, is the probability of getting a girl first times the probability of a girl second, and this right here means given we got a girl first. So this is what's called a conditional probability. Okay, so what's the probability of getting a girl second if we already have the girl first? So on the condition that we have a girl first. So let's start with just the first part, getting a girl first. We talked about it. There are 12 possible outcomes, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many of them have a girl first? Well, 1, 2, 3, 4, 5, 6. These do not. 7, 8, 9. There are 9 ways to have a girl be the speaker, right? Have a girl in the first position. Times The probability we have, I'm going to change colors so we can see what I'm doing, times the probability we have a girl second, assuming we already have a girl first, which means I can only look at the outcomes that have a girl in the first position. That would be all of these, right? Because we can't have a girl second, assuming we have a girl first, if a girl isn't first. So we have to cut out the options where a girl is not first. Okay, so that changes the number of outcomes. Now we only have 9 left. How many of those have a girl in the second spot? Well, these 3 don't, but these 6 do. So the probability of getting a girl first is 9 out of 12. That one's pretty easy. The probability of having a girl in the second, on the condition that we have a girl in the first spot, is a little bit more complicated. First, we have to eliminate the outcomes that don't have a girl in the first spot, which is why we cross out these 3, where the boy is first. So there's 9 where the girl's in the first spot, because we assumed that that happened. Then we have to look at how many of those have a girl in the second spot, and that would be these 6 that have a girl in the second spot. So those 6 out of the total of 9 give us what we want. I multiply those 2 together, I get 54 out of 108, or 1/2, 50%. Now obviously writing out all the outcomes and counting them is not the best way to do this. So there's another way, which we'll talk about in just a second. So as part of a board game, you need to spin the spinner, which is divided into 8 equal parts. Find the probability that you get a 5 on the first spin and a number greater than 3 on your second. So we got 2 events. A is a 5 and B is a number greater than 3. We're doing 2 spins, right? So on the first spin, 8 outcomes that could happen. Or get any one of these 8 things. They're equally likely. How many chances are there to get a 5? Well, just the one. We land on 5. Times how many places can it land the second time? Well, it could still land in any one of the 8. So these are independent events. So we're just going to multiply the probabilities together, right? Landing on 5 the first time does not make it any more likely to land on number 1 the second time. It makes no difference. So the second time, how many ways are there to get greater than 3? Well, that would be 4, 5, 6, 7, or 8, which is 1, 2, 3, 4, 5 of them. So that's 5 64ths, or on the calculator, 5 out of 64 is 0.078. 7.8%. Okay, let's look at a slightly different example. A bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, and then draw another bill. Find the probability that both A and B occurs. A being that you draw a $100 bill first, and B, the second one is $100. Now, these are dependent events. Right? We are not replacing the bill after we draw it. We're going to draw out 100, put it in our pocket, and draw again. That changes the probability the second time. So let's start with the first one because that one's easy. How many different bills could I draw out of the bag? Well, if there's 20 ones and there are 5 100s, that means there are 25 bills. The first one needs to be $100, so how many ways are there to do that? Well, there's 5 bills to choose. Perfect. Now for my second draw, this is where it changes. This is where the fact that they are dependent comes into play. If I put one of the bills in my pocket, how many are left? There's only 24 now. And if the bill I put in my pocket was 100, how many hundreds are left? 4. So this does the exact same thing that this example did. We just don't have to list out all the outcomes and think about it because we know how the probabilities can change if we just think through that. Okay, so that would be 20 out of 600, or 2 out of 60, or 1 out of 30. 1 divided by 30 is 0.03 repeating, or 3.33%. Okay, so another example. A quality control inspector checks for defective parts. The table shows the results of his work. Find A, the probability that a defective part passes, and B, the probability that a non-defective part fails. So whatever the test is that he's doing. So defective or non-defective, that's what he's trying to find out. Whatever test he's performing obviously doesn't work all the time. So A, What's the probability that a defective part passes? So 3 defective parts passed. We need to divide that by the number of defective parts that there were. Well, 3 of them passed, 36 of them failed, meaning there are 39 parts. So 3 over 39 is 0.077, or 7.7%. B asks the probability that a non-defective part fails. Well, non-defective failed. So 11 of them out of how many total non-defective parts? 461. So 11 divided by 461 is 0.024, or 2.4%. That's an example of conditional probability, right? What's the probability that a defective part passes? Well, it has to be defective to begin with. Okay, so a little bit more for your notes real quick. We can rewrite the formula for the probability of dependent events in order to write a rule for finding conditional probabilities. So here's the probability formula, for conditional probabilities. We're only really interested in this part. The probability that B occurs, assuming A already happened, that's what this line means. It's called a pipe. So the probability that B happens, assuming that A already happened, is the probability they both happen divided by the probability of A. Okay, so make sure this is in your notes real quick. Again, this is for conditional probabilities, so you can label it. And then we're going to look at an example of this. So pause if you need more time. I'm going to move on. At a school, 60% of students buy school lunch. Only 10% of students buy lunch and dessert. What is the probability that a student who buys lunch also buys dessert? So I want the probability that a student buys dessert assuming they already bought lunch. So I want the probability that a student buys dessert and lunch and divide that by the probability that they bought lunch, right? So we could call this B given A. This would be B and A divided by probability of A. That way we can match it back to our formula from back here. Okay. D and L in this case representing lunch and dinner. So let's just plug in what we know. What is the probability of dessert and lunch? Well, 10% of students buy lunch and dessert. So that would be 0.10 divided by, what's the probability of just buying lunch? 60.6. So I need 0.1 over 0.6, or 1/6, which is 0.16 repeating. 16.67% is the probability that a student who already bought lunch will also buy dessert. Okay. As always, go ahead and replay anything you need. Reach out if you have any questions. Good luck on the homework and have a great day.